Hello gentlemen, welcome to our video on Chapter 9 entitled The VSEPR Theory and Molecular Geometry. Now, Chapter 9 focuses on the geometry of molecules, called molecular geometry, which is the 3D shape of a molecule in space because we live in a three-dimensional world. Now, in our previous chapter, we looked at Lewis structures, which just show the connectivity of molecules that are sharing electrons, but not necessarily how it's really spaced in a three-dimensional environment. So today we're going to look at that. So, the molecular geometry of a molecule is based on something called the VSEPR theory. The VSEPR theory, VSEPR is an acronym standing for valence shell electron pair repulsion. Now this theory says essentially this, that the repulsion between bonding electrons to bonding electrons or bonding electrons to lone pair electrons will create a repulsion that will, in the valence shell, push electrons into different angles, or push the atoms that are holding those electrons in space to different angles, giving that molecule a specific geometry. So electrons repel one another and make the atoms spread out to a specific geometry and kind of lock it in that space. For example, a molecule looking like this. Here are bonds, and those bonds want to spread out as far as possible in all directions from one another due to repulsion, and you get locked into a specific geometry, like so. So today we're going to go through some examples and some foundational geometries. There are more geometries than we'll go through today, but these are the basic ones. So looking at carbon dioxide. To determine geometries, you must draw a Lewis structure. It's really helpful to do so, at least, until you really get the hang of this, but draw Lewis structures. So carbon dioxide. Now, I'm not going to go through how to draw these because you should already know. I'll just draw them and we can analyze. So when we look at a Lewis structure and we're trying to find geometry, we want to focus on the central atom. The central atom here is carbon. And when we look at carbon, we want to focus on two criteria: bonding domains and lone pair. Bonding domains is a fancy way of just saying areas of bonds around the central atoms, like bond density. Not how many bonds, just areas of bonds. Carbon is our central atom. It has two areas of bonds around it. There are two double bonds, so there are four bonds there, but areas of bonds, just two areas of bonds. So we would say two. Lone pair on the central atom, none. Oxygen has lone pair, but we're not looking at oxygen. Carbon, central atom, has zero. If you ever have two bonding domains and zero lone pairs, it locks you into a specific geometry. That geometry is called a linear geometry. And that should make sense geometrically and through electrostatic charge attraction or repulsion. If these electrons are negative and these electrons are negative, they're going to want to be as far apart from one another as possible. So if you have a central atom, far apart as possible, if you have two bonds, it's going to be on opposite sides completely. That's why these bonds here are on opposite ends of the central carbon, with oxygen being attached out here. That gives carbon dioxide a linear geometry. Okay, our next examples follow the same kind of premise, looking at where electrons are, how they're going to repel one another, and lock it into a specific geometry. I'm going to go a little faster now. So, H2O. We have that connectivity in my Lewis structure. Now, I drew it this way because these lone pair electrons are going to want to repel one another, and they're going to want to repel the electrons in the bond here. These electrons are going to force these bonded electrons down into a arrangement like so. Kind of, upside down peace sign or something like that, right? It forces it down in that kind of geometry. So we have two areas of bonds around the oxygen. So my bonding domains would be two. Lone pair, I have two lone pair on my central atom. That geometry is called a bent geometry. Next, BF3. So boron trifluoride has this particular Lewis structure. Now we know this is hypovalent. It can have less than the octet, and it's defined that way based on its formal charge arrangement. So we're good here. Now looking at the geometry, we've got three bonding domains around central atom, zero lone pairs. If you think about that, that's going to be something that's triangular in nature. So the name for this one is trigonal planar. And these would spread out, in kind of triangular bond angles here. This angle would be about 120. Not about, it would be 120. Just give me that number so you can just think about how these spread out. Now, on to some more examples. Next, NH3. So NH3 will have that Lewis structure. In this Lewis structure, I've got 3 bonding domains, 1 lone pair that's going to be trigonal, pyramidal. Because in 3-dimensional space, this nitrogen, this lone pair here, are going to be pushing down on all 3 of those bonding domains. So it's going to look like a little tripod, like a little pyramid, standing up like so, with nitrogen on top. So trigonal pyramidal. Next, CH4. CH4, sorry if this gets a little congested here. What CH4 looks like so. We have 4 bonding domains, no lone pair, so that is going to be tetrahedral. Tetra meaning 4. SF4. Well, sulfur having 6 valence electrons, but only 4 fluorines to bond to, is going to have to expand its octet. And when it does, we get this here. This, we have 4 bonding domains and 1 lone pair. It's called a seesaw geometry. We'll talk more about that in class. Now, PF5 is an example that we've done in class before. Phosphorus being able to expand its octet would make this geometry. And excuse me, I didn't draw all my lone pair electrons here. This would have 5 bonding domains, 0 lone pair. We call this one trigonal bi, that's not how you say it, spell bi. Trigonal bipyramidal. So trigonal bipyramidal. If you look at this in space, it would have 2 pyramidal kind of shapes on every side you flipped it. So one going up, one going down, but we'll build these and you can see in space what it looks like. Last one, SCl6. So this geometry, or this Lewis structure, as you can imagine, a little more space here, look like so. And imagine there are 6 lone pair on each chlorine to giving it an octet. That doesn't really matter for our discussion here today, but that's what it would look like in this Lewis structure. We have 6 bonding domains, 0 lone pair. This is called octahedral. This would be the shape of like a playing jack. Have you ever played jacks before? Get the jacks on the ground, ball bounces, you swipe the jacks. This would be the shape of a jack. Okay, gentlemen, so please take notes, come to class prepared to talk about this. This is molecular geometry, our last chapter for our 6 through 9 segment. Adios.